Thank you, Mr. Chairman, members of the Commission. I'm Bruce Landrey from NuScale Power. I'm a Northwesterner, grew up in Oregon, began my career at the Portland General Electric Company when they were completing the Trojan nuclear plant. I have some claim to Idaho. I attended the Public Utility Executive Program when I was 29 at the University of Idaho for the entire month of July. Moscow is lovely in July, I found. So this morning I'd like to share with you information on NuScale, some of the things that we see driving the small modular reactor market that may be helpful to your thinking as a commission, and then an overview of the technology and where we are in commercialization. I began working with NuScale in January of 2008, and at that time small modular reactors really hadn't even received an acronym yet. The SMRs hadn't been applied. So NuScale essentially was formed at the end of 2007. We received our first funding in 2008. Dr. Paul Lorenzini and Dr. Jose Reyes, the two co-founders, and I, when we would go to conferences or we'd go back to Washington, D.C., we'd be happy if anybody would take our business card and want to talk about SMRs or light water SMRs. Well, now small modular reactors are mainstream. This is a quote from the Assistant Secretary at the Department of Commerce about 18 months ago at a conference. You know, small modular reactors represent the innovation that is the competitive edge for this country, and that's really the case. We find that there's just phenomenal interest in SMRs, not only in the United States, but in Canada, in Asia, around the world. This language is out of the Western Governors Association policy paper on nuclear power, completed last year, led by Governor Otter of Idaho, but again, referencing the important role that SMRs can play in energy production and our economy. So what's happened in nuclear power? And this is, I put this chart together because this is what I've witnessed in my career in commercial nuclear power. I'm not an engineer, I'm a business and marketing person, but what happened in the old generation of nuclear power is that every plant was first of a kind. You know, we have 104 operating plants, and except for those that are, say, 2 twin units, every other plant is different. Every plant was first of a kind. There's no standardization. Now, with the NRC's new process of design certification, we standardize the plant design for 20 years. And with that, we get the economy that comes from repetition and standardization. As John alluded to, there used to be separate licenses for construction and then a second and operation. And that operation license was a big risk that utilities took on. Plants such as Shoreham, such as Seabrook were delayed for years. The owners had to carry the cost of those plants on their books and all of the accumulated interest, which could come to hundreds of millions of dollars a year. Now there's a single license issued at the start. A combined construction and operating license is given before the owner breaks ground. The old nuclear fleet up until the mid-90s operated at capacity factors of about 70%. Now the fleet average is in excess of 90%. Some companies like Exelon have fleet averages of 93%. Well, each 1% of operation for a 1,000 megawatt plant, that's 3.65 days of additional full power operation. It's about $5 million in power production right to the bottom line. So moving the capacity factor from 70% to 93% was huge for the industry. In the past, all of the big plants had active safety systems, right? Required emergency power, emergency backup generators. Now the designs for some of the large plants and for all of the SMRs are to rely on natural forces like natural circulation, passive cooling for cooling in emergencies. In the past, all the plants were large, 1,000 megawatts or more. And in fact, kept getting bigger in order to achieve economies of scale. Well, one of the things that didn't change until small modular reactors like NuScale came along, all the plants were big. In fact, they got bigger and bigger. They got to 1,350 megawatts, 1,650 megawatts, 1,750 megawatts, a tremendous amount of electricity on one shaft, 3 Bonneville dams on one turning shaft. Well, SMRs are changing that. What's driving the market? I think this is also important information for your Commission's consideration. You know, aging infrastructure in the United States is going to be a big factor driving the market. We have 330 gigawatts of coal from 1,100 plants. Half those plants are more than 40 years old. John talked earlier about the retirements that are taking place. We are seeing no new coal plants built in the United States. In fact, we've seen 230 plants canceled. Another factor that many aren't paying a lot of attention to, but I think is critical, is that we get 20% of our electricity now from those 104 operating nuclear plants. Even with life extensions to 60 years, all of those plants will be forced to retire by 2050. So the United States faces replacing somewhere between 40 and 60% of its existing infrastructure in the next 40 years. And then, of course, there's a lot of effort going into renewables. Renewables are great, but many of the best sites for renewables are now gone. And the more renewables we have, the bigger challenge we have integrating them into the grid. So, the drivers for small reactors, the first is safety. With smaller size, we get simplicity, we get a better opportunity to take advantage of passive safety systems to improve the safety of the design. Less business risk, right? For the capital cost, there's less money at risk for a shorter period of time. The capital cost of the plant is dramatically less. John mentioned a 36-month construction cycle that they hope to achieve. That compares to 60 months or more for a large nuclear plant. With the economies of small, and I'll talk more about this, we've been able to take many components out of the plant. So there's less to design, engineer, license, build, and operate. We also are striving for as much modularity as we can to get all of the components into a factory and manufactured there. And in that factory setting, you have people whose skills continually improve, you get quality improvements, and you get the benefits of learning by doing. And then SMRs have, in our view, a broad, accessible market. For our plant, we have designed a reactor that's 45 megawatts electric, scalable up to 540 megawatts in a utility-scale nuclear power plant. So we think that that can bring us into markets that nuclear power never could go into before. And then there are multiple applications for these designs, not just making electricity. We have tremendous interest in desalination in the Middle East, in Northern Europe, in China, in India, a lot of interest in using this technology for district heating. So, because of the belief in the economies of scale and the need to get bigger and bigger, at NuScale we've coined this term economies of small. And the acceptance of SMRs really has required a paradigm shift on the big nuclear guys, right? They've always believed that you had to have these big nuclear plants, and it's taken them a while to say, okay, maybe there is some benefit and there are some economies from small nuclear reactors. The upper picture shows a construction of an EPR in Finland. You know, you get 3,500 to 5,000 people crawling all over themselves trying to build this plant. The lower picture is an illustration of what the upper two-thirds of our reactor module would look like shipped by truck. Our peak construction workforce, for example, will be right around 1,000, a much more manageable approach to building the plant. As I mentioned, you know, simplicity. With this design, and specifically with our design, we see that there's less to develop, there's less that we have to design and engineer, less that we have to take through licensing. Once it's licensed, there's less to build, there are fewer systems to operate, and there's less to maintain. So those, to us, are the economies of small. Our company. Back in the 1990s, Oregon State, Dr. Jose Reyes, our now Chief Technology Officer, was called upon to build the test facility that was used to license the Westinghouse AP600 and then the AP1000. After that, the Department of Energy came to Dr. Reyes, and he put together a team at OSU and with Idaho National Laboratory and with Nexent to develop the MASLWR. I know you've found that as you were looking at nuclear power, everything's an acronym, right? So MASLWR was the multi-application small light water reactor. It essentially was the conceptual NuScale design. And Dr. Reyes and his team then built a 1/3 scale electrically heated test facility at Oregon State to prove out that design. When that program was over, DOE turned everything over to Oregon State, and Oregon State continued to refine the design. NuScale was formed in 2007 through a tech transfer agreement with Oregon State. 2008, as I said, we received our first funding. We established the executive team. We had our first interaction with the NRC. Dr. Lorenzini and I started going to Congress, going to DOE, telling the SMR story. Last year we received funding from Fluor Corporation. Fluor is a major investor in NuScale. We're not a subsidiary of Fluor. It's a direct investment in the company. And Fluor is a great partner for us. They have more than 40,000 people in 66 countries. They've been in the nuclear industry since its inception. They've built more than 20 plants, designed 3 of them, and they understand the industry and they understand what we're about and what it's going to take for us to get to the goal line. So what are we doing? The illustration below is of what one of our plants would look like in an arid location, say eastern Idaho, air-cooled. So we are commercializing a 12-module power plant. The idea is to achieve utility scale by clustering multiple small modules together inside the plant. And we're designing this so that it can be built in 2 increments. The first increment is putting in 1 to 6 modules sequentially to get to 270 megawatts, and then after that, adding more balance of plant to get to 540 megawatts. How it works. I have an animation on this, but due to time, I'll wait, and if those are interested, I can show it over the lunch hour, explaining how it works. But the unique thing about the NuScale design, and frankly, it's something that we are learning has more and more benefits the more research we do into it. But what we're doing is we have taken a nuclear steam supply system, a nuclear reactor that has its steam generator inside the reactor pressure vessel. You know, customarily, they're outside, they're a separate unit, right? And the reactor vessel is 45 feet by 9.5 feet, and the fuel core is inside the bottom of that. And then we have taken that and we put it inside a steel containment vessel that's 65 feet by 15 feet. So this is different than the traditional nuclear power plant where you see that big concrete dome building is the first thing built and the reactor goes inside there. Instead, we have a steel containment vessel. The space between the reactor and the containment vessel is evacuated. It's a vacuum bottle, so it acts like a thermos. That means we don't have to have any insulation wrapping the reactor. And then we take that whole thing and we put it in a 10 million gallon pool of water with the other reactor modules. And the reactors are installed sequentially, one at a time, after the plant is built, and then they're refueled sequentially. And so the most the operator ever has out of operation is 45 megawatts. The refueling cycle is every 2 years, so we can achieve very high capacity factors and very efficient operations because instead of having to bring in hundreds of people to do the refueling, all of that work is done by the plant staff. And then each of these reactors has its own independent skid-mounted turbine generator set. The turbine generator is designed to be water or air-cooled, but it's easy to transport. As I said, it's skid-mounted. It's fast installation. Some of the utilities that we're talking to have looked at this and said, well, it's great because we know what to do. We buy a spare. It's inexpensive. If there's a problem with the turbine, they can pull it out and put in a spare. NuScale also has, we have a reputation, a very positive one with the Nuclear Regulatory Commission because of our willingness to do things early on in the process that many others wait to do at the end. And one of those is not only the test facility, which we've had in operation since 2003, but we recently commissioned a full-scale control room simulator at our offices in Corvallis, Oregon. And so this models the operation of a power plant with 10 reactor modules, and it will allow us to do human factors analysis, which we're actually doing in partnership with Idaho National Laboratory. INL has a reconfigurable control room, and we're working with INL on our human factors analysis because one of the things that we need to demonstrate to the NRC is that we can competently manage all 12 modules from a single control room. This is an aerial view of what the reactor building would look like, but you can see it's like looking at an egg carton, right? A dozen reactors, each installed in their own bay in this 10 million gallon pool of water. And on the far right side, you see the spent fuel pool, and next to it in the lower right, the module assembly and disassembly area where the reactors are installed, fueled, put in place, and then later taken apart and refueled. And this demonstrates the incremental build-out option, where the first 270 megawatts of capacity is installed, and then later the owner can come back and add another 270 megawatts. Utilities really like this approach because it allows them to build a plant with a lower initial capital cost and put it into operation, start generating cash, and demonstrate that the plant is used and useful. So, we think that, in fact, we know that our design offers an extra layer of safety, so important. One of the things is that we have eliminated any opportunity for a large break loss of coolant accident. There's simply nothing large in the plant to break to lead to a large break loca. There are no design basis accidents that can uncover the fuel. We have a very robust design from a seismic standpoint. The peak ground acceleration that we're designing to is 0.5 Gs. For comparison, the safe shutdown earthquake or the maximum earthquake that the Trojan nuclear plant was designed for was 0.25 G. So this also gives us a broader accessible market. Smaller source term per reactor because there's simply less fuel in it. Low core damage frequency, 2 times 10 to the minus 8. I'll talk more about the additional barriers to fission product release, and then the very large pool of water, which is our ultimate heat sink. I just referenced the seismic design. This is the curve, if you will, but we believe that this will be a significant enhancement in safety for power plants. So in a conventional light water reactor power plant that we have today, the barriers between the fission product, the fuel, if you will, and the environment are 3. And it starts with the fuel pellet, and then the fuel rods themselves, the cladding, and then the next barrier to the environment is the reactor vessel itself, and then the third and final barrier is the containment building. Well, in NuScale's case, we've added 4 additional barriers. First of all, we've got all of the water in the reactor pool, and then around that, we have a stainless steel lined concrete reactor pool with biological shields covering each of the reactors. And then we have a class 1 seismic building, the reactor building over it, which is designed to withstand commercial aircraft, typhoons, hurricanes, and the like. So a number of additional barriers to protect the public. Fukushima led us to do quite a bit of an additional analysis, and this is an example of where we found that our design really is enhanced because of our ability to remove heat through the containment vessel into the water. So when a reactor trips, when it shuts down, it still is producing about 10% of the thermal energy it had at full power. You know, with a large reactor, it'll go from 5,000 megawatts thermal to 500 megawatts, 3 times what we have at operation. Our operation is 160 megawatts thermal, so 1 second later, that's down to, at trip, it's down to about 10 megawatts thermal, but that heat still has to be removed. So we've designed this so that the first step is to use heat exchangers on the outside of the containment vessel, which can remove heat for about 3 days. At that point, valves are open and allow water to leave the reactor vessel in the form of steam and condense against the side of the containment vessel, and for the steam to transfer its heat into the reactor pool. And then when the containment vessel floods above the reactor core, valves are open to allow that water to recirculate back into the reactor. And there's no forced or mechanical circulation required. So what would happen, though, is that as the decay heat continues to be removed by this method, after about 30 days, the water in the reactor pool, if we couldn't put any more water into it, would boil off. At that stage, however, the thermal energy is down to about 400 kilowatts, and the natural circulation of air over the reactor vessels, and we've done this analysis for all 12 reactors in this situation in the reactor pool at one time. But the circulation of air would be sufficient to keep the reactor cool and the fuel safe, and frankly, to protect the asset. So our pathway to commercialization, our goal is to receive design certification from the Nuclear Regulatory Commission by 2017. We have been working with the NRC since 2008. We're in now what's called the pre-application phase. That allows us to work with the NRC staff to identify potential issues and agree on a pathway to resolve them or answer questions before we file our formal documentation, which we will do in the next 2 years. That starts the formal process. The NRC has said publicly that they expect they should be able to review our application in 30 months. So our goal is to get the design certification by 2017 so that a customer can start building a plant and put one in operation in 2021, 2022. John talked about the funding opportunity announcement. The Pete Lyons and the Department of Energy Nuclear Energy Office have made SMRs one of the key goals in bringing them to commercialization. So over the last 18 months, they worked very hard to secure congressional support and OMB support for this commercialization licensing program. It's proposed at $452 million, starting in the current fiscal year at $67 million, and it's a maximum of 50-50 cost share, all to support licensing and design. So it's to support design certification, the reference construction and operating license, which will be the first one that a customer does, some first-of-a-kind costs, and potentially an early site permit. And we are all waiting with bated breath to hear DOE's selection of the 2 designs. Guiding the development of NuScale's technology, we have a customer advisory board of 19 American and Canadian utilities, and they include the 2 largest fleet operators in the United States, Exelon and Entergy. We also have a number of publicly owned utilities, co-ops, and generation and transmission companies, as well as the National Rural Electric Cooperative Association, some PUDs. So, our advisory board just met for 3 days 2 weeks ago in Corvallis, and they're providing us a tremendous amount of input and guidance on our design, engineering, and the overall plant configuration, how we put together training programs, how we staff the plants. Very valuable asset for us. Then we have what we would refer to as a horizontal supply chain. And being a new company, we've had the opportunity, not without having any legacy, to go out and get the A-team. And so when you think of who will make the modules for us in the United States, you think about the folks who make nuclear submarines and nuclear aircraft carriers. Those are our likely supply chain partners. And then in engineering technology, of course, Fluor is taking a big role with us. They probably have 75 full-time equivalents at work on our design. Studsvik is helping us with fuel design. I think they're located in Idaho Falls. So we've gone out and picked the very best of class in each category. And this may also be of interest to the Commission because we've looked at what we would talk about as the value chain for SMRs, and this may be where there are roles for where Idaho can find roles for itself. And it starts with our design and technology development. All of the folks that we're working with on everything from engineering to legal support, lots of work in software and codes analysis, software development, but then it's all of the manufacturing and the equipment supply for these plants. And I think a real benefit is that once a manufacturing facility is built for any of the components, because they're standardized, that's going to be a long-term facility. And the people who get jobs there are going to have great jobs for a long period of time. It's going to be of real benefit to the community that hosts it. And then when plants are built, right, it's all the craft labor and everything that goes into the plant. But once a plant is in operation, it's everything associated with operations. We're looking at staffing for our 540 megawatt plant in the range of 300 FTEs, including security, but those are nice paying jobs. In fact, I was in a meeting with a prospective customer that doesn't currently have a nuclear plant, and they were looking at the payroll figures for these plants. They said, I think I want that job. So yeah, these are great jobs once you get them into our community. If I can figure out how to switch, I have one more slide that I think might be of interest, and it shows where of the people who are now at NuScale, where they came from, what their degrees are, how much experience they have. So we put this together recently for our own edification as we've been building staff. We're up to about 150 in our operations now in Oregon. 130 of those are our Technology and Design Center in Corvallis, and the rest of us who are more administrative are at a small office in Portland, Oregon. And engineering is probably 80% of our people. So you can see that we have a lot of people who have 8 to 15 years experience, and a lot of people who have, frankly, more than 25 years experience. In a project of this nature, a lot of it is project management, so we have fewer people who, if you will, who are fresh out of school. They're doing the more fundamental work, but a lot of our senior people, and there's a lot of gray hair in our operation. There's a lot of gray hair and a lot of young people, but they're managing others through the project. We have a lot of people with doctorates, but a little more than half of our people just have fundamental bachelor's degrees in engineering. And you can see the disciplines: mechanical engineering, nuclear engineering, both about equal, chemical engineering, electrical engineering, civil engineering, and physics. So that's the breakdown of our staff. And now I'll be happy to answer questions. I hope that was helpful.
Oh, it's very helpful. Thank you. Members of the Commission, what questions do you have? We just pushed you too hard and everyone's ready for a break? Or Mr. Kotek?
Thanks very much. That was an excellent presentation. At the end of the day, I've got to imagine what you all are interested in is seeing orders for your product. And from what I've seen with the large plants that are being built in the Southeast, for example, and with other proposals around the country, cost of capital has been a real big issue, plus the duration of time over which that capital is tied up, and you're clearly addressing the length of time question with this design. How about the cost of capital question? Are there things that the states or the federal government can do to help address that issue?
That's a great question, and it's particularly important with capital-intensive projects, which nuclear power plants are. A change in the cost of capital can make a big difference in the life cycle cost of the power from the plant, because you're carrying a large amount of debt or paying back equity over a significant period of time. And for example, a 1% change in the weighted average cost of capital can mean a difference of 2 cents a kilowatt hour in the price of power for the plant. Huge. So some opportunities are to lower the cost of capital. One, and it came up in the prior discussion, are long-term power purchase agreements with federal facilities, whether they're DOD or DOE. That, I think, is part of what the interest is at Oak Ridge National Lab, is a long-term PPA with the Tennessee Valley Authority for power from the plant that B&W is proposing to build there. So there is opportunity for that. Any type of tax-free financing, anything that can lower the cost to the owner of the plant. And we're in, as vendors of nuclear reactors, we're in a little odd position because our goal is simply to sell the equipment. But what I found since I've started working in this part of the industry is what we really do is try to facilitate bringing together the different parties, the owner-operator, the off-taker, the engineering, procurement, construction company, in order to make the projects happen. It'd be very different, for example, if we were selling gas turbines like GE. GE, the phone rings and somebody orders 2 frame 7s and you deliver them to a plant someplace. But we really work, really have to work to support all aspects of this. So lowering the cost of capital would be very helpful. Right now, the DOD facilities are able to sign long-term power purchase agreements for renewables of up to 30 years, but they do not have that capability with nuclear power because it doesn't fall under the category of renewable, but it would fall under the category of clean.
That was a great question, by the way. Thank you. Dr. Nellis and then Senator Craig.
Mr. Chair and
Oh, you're welcome.
regarding capital and return on size of the plant, the 540 megawatts.
So a fully built-out 540 megawatt NuScale plant would be in the range of $2.7 billion. A large light water reactor, an AP1000, which Westinghouse requires the owners buy 2 of them, but a single unit there might be $5 to $7 billion. So we look at this as having less total capital at risk for less amount of time. On the financing aspect, though, every owner is different. If it's an association of municipal systems, they may be able to finance it 100% tax-free debt. TVA can do that as a federal agency. An investor-owned utility like Idaho Power would have some ratio of debt to equity that it achieves. Maybe it's 60% debt, 40% equity. The debt would have one interest rate on it. The equity would have a return on investment of whatever would be allowable by the Utility Commission. Usually it's in the range of 10%.
Thank you, Mr. Chairman. Bruce, thank you for that presentation. A couple of questions. In your presentation, you referenced our lab a couple of times in the working relationships you've had. And this is not to be critical of our lab at all. It's to try to establish the relationship you've had. Have you found during that relationship any difficulty in your association because of federal requirements or because of restrictions between a private entity doing R&D trying to work with a federal entity?
I think the one restriction that I see personally, but it's an understandable restriction, is that the work that the labs, any of the labs do for us, has to be suitable for any other technology, similar technology, and the results need to be available to them. So we're not able to work really with the labs on things that are just specific to our design.
Proprietary type.
Proprietary type.
Might ultimately be.
But we did, at the end of last year, hire Dr. Dan Ingersoll out of Oak Ridge National Laboratory, and he's now our Director of Research Collaborations. And I know that Dan's been over to Idaho, I think at least twice, to meet with them, and Dan is working hard to work with the labs to identify research collaborations.
Okay. Secondly, playing off from Dr. Nellis' question about costs and use of capital, in your presentation, the configuration you're proposing for your modulars is plugging in multiples, if you will. I assume while building the entire, potentially building the entire infrastructure for a 540, obviously not starting with 540, does that not change, therefore, cost of capital if in fact you can start bringing units online for utility, and you may build out the basic structure, but you may not plug all units in for a period of time based on load and load demand? And doesn't that help, or would that help, I guess is a better question?
Yes, we think it will, and that's why we've taken that particular approach, to be able to allow someone to only build half of what's referred to as the balance of plant.
Right.
And then to put in one module, begin generating cash flow, demonstrate that it works. If it's a regulated utility, potentially having the investment thus far put in rate base because the plant is then declared used and useful. Mm-hmm. So we hope that provides a smoother pathway for the owner-operator.
This may be a proprietary kind of question. If it is, just smile. To build the base infrastructure for a full 540, but maybe to plug in 2 or 3, you mentioned a X billion-dollar cost for 540. That obviously scales back, I would guess, substantially, does it not? And if so, by what increment?
It is proprietary.
Thank you. All right.
But it does scale back significantly.
Sure.
Yeah.
Thank you. Thank you, Mr. Chairman.
No, thank you. Any other questions? Oh, do you have time for the video?
Oh, absolutely.
We have a request for that. Let's go ahead and finish with that then. Okay.
Disposal.
All right, thank you.
This video demonstrates how the reactor operates, and you can see the control rods were just pulled out of the fuel core. The core starts, the fission process begins, heats up, begins to heat up water. As the water is heated, it loses density, so it rises inside this flume inside the reactor vessel. It's pulled out over the top, and then it passes over these helical coil steam generators, turning water in those generators into steam. As it does that, it's exchanging its heat. The water then gains density, becomes heavier, and gravity pulls it back to the bottom of the reactor, where it simply recirculates over the fuel another time. As the steam is created, it is used goes through 2 steam lines into the turbine, which then turns the electrical generator. And that moved through it quickly. But when we talk about small, for example, if you've been through a large nuclear power plant and you look at the lines that carry the steam to the steam generators and the steam lines out of the steam generators into the turbine, they're big enough that you can walk through them. Our steam line is 10 inches in diameter. The feed water line that takes the water back from the condenser is only 3 inches in diameter. So a real benefit of having small. And this animation shows the process for installing the reactor modules inside the reactor building. So this central building is the reactor building, housing both the reactors themselves and the spent fuel pool. It also has the control room below grade. So all of the safety-related equipment is in this building. The reactors are shipped to the plant in 3 large components. The first component is the bottom of the reactor vessel itself. And you can see here it will be lowered into the reactor pool. The spent fuel pool is to the left. In this animation on the far right, you can see that there are already 3 reactor modules in place. And the next step is to bring in the lower portion of the containment vessel. The whole systems, when they're placed in the bays, they don't rest on the ground. They're actually suspended by a trunnion, which allows for some movement, some small amount of movement, should there be an earthquake. So it's part of the seismic dampening effort. And each of these components is placed in specially designed cradles. And once the lower containment vessel is in and the lower reactor vessel, the fuel is placed inside the reactor vessel internals. So new fuel, of course, is brought to the plant before the reactor vessels, and it's placed in the spent fuel pool. The spent fuel pool also houses new fuel. And then the final component to come to the site is the upper portion of the reactor vessel and containment vessel. This is one combined unit. There's pretty much nothing in the space between the reactor vessel and the containment vessel, but all of the reactor components, including the steam generators, are housed in this upper portion. So it's lowered, it's upended and then lowered, and then the bottom portion of the reactor vessel that contains the nuclear core is attached. All these components are flanged and bolted. Then the lower third of the containment vessel is attached, flanged and bolted, and the system is moved into place, into its reactor bay. And then the biological shield is placed over top of it. Thank you.
Oh, thank you. We have one other question, if you don't mind.
No, thank you, Bruce. Thanks for that presentation. I'd ask this, and I guess as John left, because I like both of your opinions on this. But presumably, you know, when nuclear energy started in this country and the world, we didn't start out with 1,000 megawatt, 1,300 megawatt plants. As you say, and as John has said, we scaled those up because of economies of scale. So presumably at that time, we could have pursued small. We could have pursued modular, but we didn't. What's changed? What now, the factors that drove us to not do it then, what has fundamentally changed that either makes this possible today that wasn't possible to then, or is somehow more important?
And I'll be speaking personally here, and I'll be speaking from my experience on the business side of commercial nuclear power. I think what's changed is first of all, the ability and realization that we can achieve the same economies or better with a small reactor as we can with a large, especially taking the approach that NuScale is, where we cluster them into a utility scale power plant. I think the other thing that didn't change but really needed to is the business risk that's associated with gigawatt scale nuclear power plants. I had left PGE and gone to TVA when Trojan was closed, but my perspective is that Trojan was closed not because it was a bad nuclear plant, but because of all the business risks that that plant posed for Portland General Electric. You know, every time that plant went down, and I handled all of the issues, the non-engineering related issues to Trojan for almost 20 years. Every time that plant went down, it was a penny a share in earnings per day. It was on the front page of the paper. We were before the Utility Commission begging, asking for replacement power costs, and we'd end up in hearings, and whose fault was it? Should the shareholders bear the cost, or should the customers bear the cost? And it just became, that plant just, the entire fate of Portland General Electric hinged on whether Trojan was operating or not. And I think that if you look at the capital costs of the new plants today, and J.P. Morgan did an interesting graph, which I probably should have included, but they compared the capital cost of the new nuclear plants to the market capitalization of the companies that are building them. And with the exception of the two largest nuclear utilities, the cost of the plants exceeds the value of the company. And so it's a bet your company risk. I think that by demonstrating that we can achieve equivalent or better economies and taking so much of the business risk out of the option for the owner, I think is really what's driving the interest in SMRs. And then if you start looking at siting flexibility, you know, all of the coal plants that need to be retired, and NRECA, the National Rural Electric Cooperative Association, joined our customer advisory board because its members are predominantly coal. And in their view, many of those coal plants are in places where they'll never be able to get natural gas. But they do have infrastructure in place, water, transmission, and if they can replace that coal plant with a scalable SMR, they can achieve some great economies.
Excellent points. Great question. Any additional thoughts? Any other questions? Okay. Mr. Landrey, thank you.
Thank you.
And thanks.